Okay, in this video we're going to illustrate the use of Mathcad to solve a problem that we had looked at in a previous video, and we had just sketched out the solution. We hadn't actually done any computation on it. And that problem was a double cantilevered half ring, where at this point we had previously had a cantilevered section just like the left half, but because that's statically indeterminate, we replace this cantilevered support with its equivalent static reactions, and there are three of them: a vertical reaction, a horizontal reaction, and a moment reaction. And because it's statically indeterminate, I can't solve for any of these reactions independently, and so I'm going to use Castigliano's method. In this case, I've got three indeterminate reactions. I'll have to write three equations for deflections for each of these and set them equal to 0 in every case, because each one of those deflections or reactions causes a 0 deflection. Once I know the reactions, I can then also solve for the deflection at this point. So as we did earlier, we're going to, in Mathcad lingo, we're going to write a function as a function of the angle theta. This is called M1. This is the moment in region 1. And the moment in region 1 will have a term caused by the vertical load, RBY. And as we saw earlier, because its moment arm is roughly this length right here, that's outside the triangle, and that's a 1 minus cosine theta term. And then the X part causes a deflection and causes a moment because of this horizontal loading. The vertical moment arm is the sine of theta term, and it's minus because it's in the opposite direction of the first term, RBX times R sine of theta. And then finally MB causes a moment opposite of the first term, so we'll say minus MB. So we've written a Mathcad function that gives us this moment as a function of theta because of the three terms. Now we're going to use Mathcad to take the derivative of moment number 1 with respect to MB, that gives us a minus 1. The derivative of moment number 1 with respect to RBX, that's a minus R sine of theta. RBX minus R sine of theta. And then finally the derivative of moment number 1 with respect to RBY, which gives us the 1 minus cosine of theta expressed as a minus cosine of theta minus 1. And then finally, when we finally want to get the deflection because of force F, we'll have to take the partial with respect to force F, and for this particular moment term we get a 0. Now in the region, once we cross 90 degrees, here's the angle theta showing larger than 90 degrees. We're going to have all of the moment terms that we began with, and so I can say that moment number 2 is moment number 1, then minus a term caused by the load F. The load F is going to cause a bending moment through this distance right here, and that will be the sine of the angle theta. But this small angle theta in here is my large angle theta minus 90 degrees from this segment. So this moment in region 2 is moment in region 1 minus F times R times sine of theta minus pi over 2. Asking Mathcad to print out the entire term, it will expand the M1 term for me, and it'll show me all of the pieces of moment number 2 without hiding it inside of M1. Now I can take my derivatives of moment number 2 with respect to MB. I get the same thing that I did before. Derivative of moment 2 with respect to RBX, I get the same partial. Derivative of moment 2 with respect to RBY, I get the same partial because the new term here doesn't involve any of those terms. But finally, the moment derivative of moment number 2 with respect to F, I do get a term. Notice all of these partial functions I'm also writing as functions of theta. So I'm creating a new function named dm2 of theta is equal to the derivative of M2 with respect to MB, which was a function of theta. And this function of theta is a minus 1. This one is actually a function of theta. And so is this one. And so is this one. Now that I've written my moments that cover the entire region, and I've written my 4 different partials for each region, that means I can write 4 different deflection equations. Some of those deflections are known because of what they do over here. They replace supports that had known behavior. No deflection in the X, no deflection in the Y, no slope deflection. This one isn't known. That's an unknown deflection that I want to solve for. So using all of this stuff up above, we'll now go write our energy equations. And there are 4 of them, and this is going to be very compact in Mathcad. So this equation says my integral over the first region plus integral over the second region, moment 1 times the partial with respect to MB, moment 2 times the partial with respect to MB. Plugging those in gives me the deflection at the point where MB is applied and in the direction of MB, and that would be a slope deflection. And I know that that deflection is 0, so I set it equal to 0. This integral will give me a large function of MB and all the other stuff. Once it's integrated out, it's going to be big and ugly, but Mathcad can do it just in this form. Set it equal to 0. That's one equation to be solved. Another equation to be solved is the deflection, and I notice I'm taking partials with respect to RBX. So these are X direction deflections at the cantilevered support, and that deflection is equal to 0. So I set it equal to 0. And I'm going to be able to solve for RBX and other stuff. Finally, my deflection due to RBY. This is the vertical direction deflection at that support location, but I know it has a deflection of 0. But this will give me, after much work, much math, an equation that involves the RBY and the RBX and the MB. These 3 equations can be solved simultaneously for the 3 unknown loads. But while I'm at it, I might as well write another true statement that says the deflection, and since I'm going to take partials with respect to the load F, this will be the deflection at the point where the load F is applied in the vertical direction is equal to 1 over EI times this integral. This integral is going to involve, because of the moment 1 and dm1, this is going to involve RBY, RBX, and MB. And so will this one. When I ask it to solve all 4 of these equations simultaneously, and I'm going to ask it to solve for MB, I'm going to ask it to solve for RBX, and I'm going to ask it to solve for RBY, I'm going to ask it to solve for the deflection at the point where the load F is applied. It will do all the integrals. It'll set those integrals equal to 0 in 3 cases. It'll set this integral equal to delta. It'll then solve the 4 unknown problems and totally eliminate these variables. It'll solve for these variables in terms of only the things remaining being the force, the radius, and trig stuff. This first term is MB. This second term is RBX. This third term is the reaction at the cantilevered support in the Y direction, which we knew had to be F over 2. It came out that way. And this is the deflection in the vertical direction at the point where the load F was applied. And so scrolling down and summarizing, simply repeating what each of those terms were. Okay, in 2 pages of fairly straightforward Mathcad, it has done a massive amount of trig and integration of trigs and algebra and simultaneous solutions of equations to give us very straightforward looking solutions for unknown support loads. This is the value of the moment, the value of the reaction force, and the deflection at the point that I'm interested in.